say that I forgot to say in the definition of fan that it's a finite set of cones. So a fan is a finite set. So I forgot to say that it's a finite set of cones. Such that. So now I want to talk about flag varieties. So I can take G, a semi-simple group, so for example SLN, SON, etc. And so definition, proposition. So an homogeneous space G mod P is complete if P, if and only if P contains a Borel subgroup of G. So maybe I have to define a Borel subgroup of G. So Borel subgroup is a maximal and so closed and connected. So maximal with these properties. So for example, take SLN. So we can take Borel as the triangular matrices. So upper triangular matrix.
The solvable is English.
Solvable, yes. Ah, yes. Solvable. Sorry. So, and then, so when G mod P is complete, it is called a flag variety. It is projective and smooth. So it's a projective variety. So algebraic variety. Okay. And yes, and P is called a parabolic subgroup. Okay, so now I want to explain more about semi-simple groups. So it's there are algebraic groups. So I want to explain the combinatorics of such groups. So I will use it in all my lectures. So that's why I wanted to explain it more or less in detail. So I take group G, and I will, at the same time, I will do the example of SLN. So we've seen we can choose Borel the upper triangular matrices. So I can note that I can say that all Borel subgroups are conjugated. So if we choose one Borel subgroup, then we will have all flag varieties. And so we can fix a Borel subgroup, it's not restrictive. And we also look at maximal torus in B, so we have inclusions. And in the case of SLN, so the maximal torus of a maximal torus of B is the diagonal matrices, for example. Okay, so maximal torus. So it's isomorphic to C star the power n. And then I can look also at the Lie algebra. N-1, yes. Thank you. So we can look also at the Lie algebra of G, which can be seen as the tangent space at the identity. And so in the case of SLN, we'll have the matrices, the n by n matrices with trace equals to 0. Okay, and here we have what we call the Leigh Brackett. And the Leigh Brackett in this example is just so the difference of the different products, so the commutator of x and y. So I don't recall here the definition of a Leigh Brackett because it's too long to write. But so if you don't know this, just admit what you mean. So just look at this example and do things with this example. So now we can look at so the adjoint representation. So either in G or in G. So we can also look at this. And here it will be so H. So it's just the conjugation. And here it's just the Leigh Brackett y x associate the Leigh Brackett x and y. So it's the same in some way. And sorry. I don't think that.
Not automorphism G, but endomorphism.
Endomorphism. Yes. So in particular, we can look at T I associate, so it's a Lie algebra, and we can do the same with B. So for SLN, it will be so the upper triangular matrices with trace null and the diagonal matrices with a trace null. And we can look at we can restrict this map to T, and so it's the same map, and we can diagonalize this morphism, and so we can write G as T plus so the sum of eigen subspaces. So I denote H alpha for alpha in some spaces. So G alpha y each G alpha. So let's look at the example of SLN. So in SLN we can look, for example, at the matrix I denote by EIJ, which are the matrices with 0 everywhere except in the line I and the column J. So here we have a 1 and 0 everywhere. So this is so for J, for A different from J. If not, we don't have a trace equals to 0. So and we can look at the action of T, so of diagonal matrices on this. So if I take H in T on this element, so I look at H EIJ minus EIJ H, and you can see that it's so you can compute that it's so I note H equals to T1, so it's a diagonal matrices of T1 Tn, and it will be Ti minus Ti minus Tj Aij. So in fact it acts with a weight which I called alpha ij of H equals so the coefficient I minus the coefficient J. So I don't know why T H. So Hij is called a root, and so it's a morphism of Lie algebra from H to C. Donc c'est you as Lie algebra morphism. Okay. So in my example here we have R equals to the set I different from J between 1 and N, and G alpha is equals to C E alpha J. Alpha Ij is equals to C times Eij. So it's one-dimensional space, and it's also true in every case. So we always have a one-dimensional space here for all alpha, and the alpha here are called roots, and it's some weights of the Lie algebra of the torus. So it's roots of the system of G and T. Okay. And in fact, if we look at the eigenspace of weight 0, it's T, because T commutes with every of each element. So if we apply T to if we do the Leigh bracket of 2 elements of T, it's 0. Okay. So now we have we can also do the same with B, and if we do the same with B, it will be equals to T plus some subspace of some G alpha for some alphas, and we define R plus as the roots such that B is equals to this sum, and R plus is the set of positive roots. And so in our example, the positive roots are just the alpha ij, where I is smaller than j. So for SLN, we have R plus is a set of alpha ij for I smaller than j. And then we can denote by R minus, so the complementary of R plus. And a result is that R minus is in fact, so it's the fact, that R minus is minus R plus. So it means minus alpha for alpha in R plus. So here it's R minus will be for A greater than J. And we can see that if we exchange I and J, we obtain exactly the inverse, the opposite of this root. So you can see that alpha ij is equal to minus alpha ji. So, and it's true in every case. So an R minus is a set of negative roots. So, and now I have to also introduce S, a basis. So it's unique, so the basis of R plus. It means that all alpha in R plus, so if S equals to alpha 1, alpha n, all elements of all positive roots can be write as a sum of A alpha AI alpha I equals to 1 to n with AI in a positive integer. So in that case, we see that so we can choose the set of alpha I, which is alpha I plus 1 for so I between 1 and n minus 1. So in that case, we will have only n simple roots. Yes, so I don't define simple roots. So the element of, so the alpha I are called simple roots. So it's the element of the basis. Okay, so here we have n minus 1 simple roots. And if we take alpha ij, we can write it as alpha I plus etc. plus alpha j minus 1. So we just write alpha I minus alpha j as alpha I minus alpha I plus 1 plus alpha I plus 1 minus alpha I plus 2 and etc. So okay, so now I have to introduce more combinatorics. So I take, I look at chi, so big chi of, so or chi of t, so the set of characters of t. Of t, it means so the set of algebraic group morphism from T to C star. So okay, and I take G dual, So it's dual. So it's so the homomorphism of Z of chi in Z. So it's dual, and I denote by this double bracket the scalar products of the pairing between chi and chi dual. So in fact, there is a correspondence between character of big T and character of the torus T here. So, but well, there's so in all cases for SLN, for example, there is a bijective correspondence, but in general there can be small difference. But I will explain this later. So then we have. So I have to introduce also another group, which is a Vi group, called the Vi group. So it's a finite group defined as a normalizer in G of T, quotiented by T. So the normalizer G of subgroup is defined by the set of G in G, such that so G minus 1 T of G is included in the subset of T. So it's stabilized the T. And for SLN, we can compute this group, and we will see that W is the symmetric group Sn, and we can represent it. We can see it as so the set of permutation matrices. So in permutation matrix in SLN. So the matrices with so for example, I can look at this this particular permutation matrices. So I put here -1 because I want that the determinant is 1. So this is the transposition I plus 1. Okay. More generally, so we have all permutation matrices. So it's finite group. And in this finite group, we have very special representatives. So we can look at G alpha, so the group, so the subgroup of G with Lie algebra equals to T plus G alpha plus G minus alpha. So, for example, for SLN, so we will have G alpha ij is equal to so the set of matrices with something on the diagonal, and on the IM line, on line I, we have some coefficient here, and 0 here, and so maybe I put and on column J we have something, and then we have 0 here, and we have the same here, right, and 0 everywhere. Okay. No, we don't have 0 here. Sorry. we have star everywhere in the diagonal, sorry. And we have some star here, so we can put, and with trace equals to 0. So this is the G alpha. And in this G alpha ij, we can see that there is only one permutation matrices which corresponds to the permutation. So I denote it by S alpha ij. It's so the transposition ij. So it's a unique element in this group. So unique. So unique permutation matrices in G alpha ij. And more generally, for all, here we will have a unique S alpha in W, such that S alpha has a representant. So here we have a quotient. So when I say that W is the permutation matrices, I just said that it can be each element can be represented by a permutation matrix. And so in that case, we have S alpha in W, such that it exists a representant of S alpha in the normalizer of T, and in particular in G alpha. Yes. Okay. So and S alpha is a reflection. So as for SLN, so it's a transposition. So if we take the square of it, it's the identity. So and this is for all alpha in R, and so it's symmetric. So we can do also this only for positive roots. And yes. And if we take simple roots, so we will have this transposition. And it is well known that the symmetric group Sn is generated by transposition I plus 1. And it's also the case for W, for all Vi groups. So the Vi group is generated by S alpha for alpha in S. So only the simple roots. So we have only to take the basis of the positive roots. So, and then there is another result which says that there exists a unique. So I said that S alpha is a reflection. So we can write S alpha of X as X minus something times alpha, and this will be called X alpha dual, and there exists a unique alpha dual such that first alpha dual and alpha is equal to 2, and we can express the reflection as this difference. So this is a number. So this is the pairing I use here. So alpha dual is in chi dual. So maybe I can give the maybe I let you a little time to write what, and then I will project some slides. So I can say that so R dual. So we can do. So here we can do for alpha in R. So it's true for all alpha in R, and we denote by R dual. So the set of alpha dual with alpha in R. So in alpha, it's called the co-root of the system. And so here we have the set of characters, and the dual of the set of characters are called the co-characters. So it's just terminology, co-characters. Okay. So it's just names. So maybe I can give the example in rank 2. So I didn't tell what is the rank. So the rank is the rank of G is the dimension, the cardinality of S, which is the number of simple roots. So for SLN, so the rank of SLN is n-1. So it's also the dimension of the torus. No, it's not this. So I. Oh, yes. So I do not tell what are the type, but we will see it later. So the first one corresponds to SL2 times SL2. So here we have two roots, two positive roots, alpha 1 and alpha 2, and also two simple roots. So it's very simple. Maybe the most interesting example is for SL3. So here we have alpha 1, alpha 2, and we have also alpha 1 plus alpha 2. So if you remember, we have alpha ij equals alpha I plus alpha j minus 1, and in that case we have only 1 and 2, so we can only have this, and we represent it here. And so for the representation we use scalar products such that so alpha and alpha equals 2. So the and with this convention, we will have alpha 1 equals alpha 1 dual, and alpha 2 equals alpha 2 dual. So this case, so the case of SL3 is very, very simple. So I don't define the omega 1 and omega 2. So omega 1 and omega 2 are just the dual basis of, so we can take so the dual of simple roots. So it's a basis of the space, and we can take the dual basis. So this is the basis of the co-characters, and we take the dual basis with respect to this, and we will have the so-called so omega alpha, so alpha in S, and we call them fundamental weights. So there are in okay. So well, this is not really true, but I will explain this later. So if we take the characters of the Lie algebra of T, it's okay. It's true, but if not, so we have to suppose that G is simply connected. But for SLN, it's true. So in particular, we have omega alpha change equals to beta change. So 1 if alpha equals beta, and 0 else. So in the other example, it's SO5 and G2, and in these examples we will have so we will have this condition only for small roots, because we have small and big roots. So because this root is smaller than this one, and in this example we have so all roots have the same norm. but in other examples it's not true. And so that's all the diagram we can have in rank 2. So we can represent them like this, and yes. And then we will have a formula which says that alpha, I don't remember, that alpha, beta, so we can, so this is the products, the scalar products on R2, so the canonical scalar products, and we have formula like this. I don't remember, no, it's not like this. What? So we have formula between so the scalar product here and so the product alpha, beta dual. But this is symmetric and this is not symmetric. So maybe I just so I will use another slide in a few minutes. So I let the screen here. So now we want to give types of groups to classify them. So that's I want to define a Dynkin diagram. So a few remarks here. When we are in dimension 2 here, we have 2 here, 2 here, 2 here, and 1 plus 1 equals 2. So we have this parameter 2, which corresponds to the simple roots. So a Dynkin diagram is a graph with vertices of G. Vertices, the elements, so the simple roots. And with arrows. So, like this. So we have an arrow between alpha I and alpha j if so the product alpha I and alpha j dual is equals to 1, and the same alpha j dual alpha j alpha I dual equals 1. We will have a double arrow. So if we have 1 here and 2 here, or do you see? No, maybe not. So if so we have a product here equals 1, and the other, so alpha j alpha I is equals to 2, or the inverse. So it determines if the arrow is in this direction or in this direction, but I didn't remember what sense it is. And we will have 3 arrows if we have the same thing. So there is minus everywhere, sorry. And so we have a -1 and -3. And other cases are not possible for algebraic group. So we can construct all diagrams with these things. And we have, so there's diagrams when they come from a group, a semi-simple group must satisfy a lot of conditions. And with these conditions, we can classify all the Dynkin diagram we can have. So that's we call the type of the group. So we have 4 infinitely families, which correspond to type A, B, C, and D. So maybe I can just say that the type AN, so N corresponds to the number of vertices, corresponds to SLN. Bn corresponds to SO to N plus 1. Cn corresponds to the symplectic group sp2n, dn corresponds to so2n, and the other type are called exceptional groups. So for each diagram we have exactly no, not exactly one group, but finitely many groups. So maybe here I want to say something on the group. So the Dinkin diagram classifies the semi-simple Lie algebra, but it does not classify entirely the semi-simple groups, because for each Lie algebra we can have several groups. For example, here we have several groups, and we have, for example, PSLN. So if we look at PSLN, which is SLN quotiented by the center of SLN, which is diagonal matrices with units of with roots of unity. So the same root of unity. So we have so the center is lambda with lambda at power n equals 1. And so we have several groups, and here we have also the that we call spin to n plus 1, and etc. And here we have also a non-trivial center. But in any case, we have a maximal group, which is simply connected. So SLN is simply connected, spin to n plus 1 is simply connected, and we have a minimal group which have center trivial. So which have trivial center. So for each diagram we have finitely many possible groups, and generally we use simply a connected one, because it's the one who has the most of information. For example, if we look at in the case of SLN, if we look at omega alpha, so the fundamental roots, so we can compute that so omega alpha I in the case of SLN, so if we applied it to the torus, so an element of the torus, so the diagonal matrices with T1, Tn, we can see that it's the product of T1 and T2 and etc. and Ti. So if we look at alpha 1, omega alpha 1, the first fundamental weight, so it will be T1. But now, if we want to do the same with PSLN, we will see that this character is not defined, because so it's not defined because we have quotiented by this form on, and it's not so how to say this. So it's not defined because it's not trivial on the center. So if on the center this is equals to lambda, and lambda is not 1, and so you can't quotient this character. So this is the definition of this character. So in general, we also assume that the group is simply connected, and we won't have a problem like this. So all fundamental weights will be weights of the torus of the group. And then the weights of the torus of the group is the same as the weights of the Lie algebra of the torus. And then all the classification works very well. So, okay. The Borel subgroup are conjugated, so we fix a Borel subgroup, so we take G and we fix B, and we want to classify the flag varieties. So it's equivalent to classify so parabolic subgroup containing B, and it's in fact equivalent to subset of the simple roots. So S is the set of simple roots, and for each subset of the simple roots, we have a parabolic subgroup. So maybe, yeah. So how do I do it? Okay. So maybe I do the example of SLN. So in SLN, so if we take the parabolic subgroup, so we take the upper triangular matrices. So this is B, and we have. So we want a subgroup, a closed subgroup, which contain this subgroup. So we don't have a lot of choice, so we have to do triangular matrices, so block triangular matrices like this. So that's the only thing we can do. It's this. So it's so P. So this is SLN. So P is block matrices. So triangular. So triangular block matrix. So upper triangular. And you can see that. So you can look at the moments where you decide to. So we can look at this point. So the moment you are in the diagonal here. So the moment when you have a step, and this defines a subset of the simple roots, because simple roots are alpha I, alpha 1, and to alpha n minus 1. So we can classify all simple roots with the coefficient in the diagonal under, so the line under the diagonal. And for each point here, it corresponds to a simple root, and it corresponds to this simple root. So in particular, if we take I equals to nothing, it will be okay. So that I want it okay. So I take I, so in this example, I take I to be the cross here. So we have to take a convention. So I is the set of cross, and then S minus I is the set of points. And with this convention, so we have I equals the empty set if only if P equals B, and I is equals to S if and only if P equals G. And we have all parabolic subgroup in this way. And we can also remark that Pi, so I denote Pi, the parabolic subgroup corresponding to I, and Pi will be Pi included in Pj if and only if I is included in J. So we have a total complete description of parabolic subgroup. Okay, so yes. So we have a very nice description of flag varieties, and a lot of results are known on flag varieties. And we often use Breuer decomposition, which is a decomposition into B orbits, so into orbits under the action of the Borel subgroup. So we have G can be decomposed in B orbits, so double orbits, so B acts on the left and on the right. And it's indexed by the elements of the Vi group. So there is finitely many orbits. So in particular, there is an open orbit. So corollary is yes. And we can also take G mod B here and G mod BWB mod B here, and it's also true. And there is so finitely many orbits, and there is an open orbit, and this is a nice property. So G mod B has an open orbit under the action of B. And in fact, this property will be the definition of spherical varieties. That's why I point it here. So we can also have the same, a similar decomposition. So it's a cellular decomposition. So each BWB mod B is isomorphic to an affine space. And if we take a parabolic subgroup instead of B, so we have a similar result. So with also cells isomorphic to the affine space. But here we have to index by a quotient of the Vi group, which I denote by W mod WP, where so B WP mod P, and here WP is just the subgroup of W generated by the S alphas, where alpha is in S minus I. No, I. Sorry, in I. So we have, if I is the empty set, WP is trivial, and then we have the property for G mod B. So this is a subgroup of W. So then we have a very nice decomposition, and this decomposition is very useful if we want to compute the cohomology of flag varieties, for example. And so the closure of the cells are called Schubert varieties, and the cells are called Schubert cells. And so we have an open orbit, and so the open orbit corresponds, so B orbit, so the open B orbit. We have only one open B orbit. We can't have several ones. So we have only one open B orbit, and it corresponds to a special element in W. We called it W0. So it's the longest element in W. So why do we call it the longest element? Because we have a definition of length in W. So recall that W is generated by the S alpha in alpha in S. So we can define the length of an element as the minimal of the number of simple roots we need to write W as S, so alpha I1 S alpha IR. We can write W as a product of simple reflection, and we take the smallest number of such of simple reflection and then by this way we have the codimension of X W is equals to the length of W. So in particular the length of No, it's the dimension, sorry. The dimension of, so the L of W0 is equals to the dimension of G mod P. Okay. Okay, so what can I say? So in particular, we have the B-stable divisor of a G mod P corresponds to the set of X W0 S alpha for alpha in S minus I. So if alpha is in I, then S alpha is in WP, so W0 S alpha is the same as W0 in this quotient. So that's why we only have alpha in S minus I. So in particular, the Picard number, you can compute the Picard number of G mod P. And it's equal to the cardinality of S minus I. And rho is equals to 1 if and only if. So we have only, so I is equals to S minus 1 root. And for example, so always SLN, and we question by so we have only two blocks on the diagonal, because we have S minus 1 is of cardinality 1, and F minus 1 was the point here. And this is the Grassmannian. So if we have dimension I here and I here, so it is the Grassmannians of I-dimensional subspace in Cn. So it's okay. So so maybe I just I just say two geometric properties of flag varieties. So the first one is that G mod P are locally rigid. So it does not admit local deformation. Or in other terms, the cohomology in degree 1 of the tangent bundle is 0. So in fact, we have this for all I strictly than greater than 0. So it's the first remark. And the second remark is that G mod P are Fano varieties. That's two nice properties of flag varieties. So I have not finished with flag varieties, but maybe I can do this tomorrow morning. So I stop here.